This is the third session of our webinar series on graph theory. Today we have with us Professor Jason Brown. With great pleasure, let me introduce Professor Jason. Professor Jason Brown is a professor at Department of Mathematics and Statistics at Dalhousie University, Halifax, Canada. It's 9 AM today, local time there. His areas of interest include chromatic polynomials, network reliability, independence in graphs, simplicial complex, and mathematics and music. He has published around 100 research papers in reputed journals, and he is very much interested in research in mathematics and music. In fact, he is the first person who established a relation between independence polynomial and fractals. That's how I invite him for this seminar series. So on behalf of the organizing committee and on behalf of all the participants, Professor Jason may invite you to deliver the lecture on getting back to your roots. Professor Jason, please.
Thank you very much, Professor Kumar. It's a pleasure to be speaking to everyone from Halifax, Canada. I'm on the East Coast, and I hope everyone is keeping well and safe. So the title of my talk is Getting Back to Your Roots. And I've been working in graph polynomials for many, many years, a variety of them. And I'm going to talk in particular about one kind of polynomial in this talk. So let's begin. There are many polynomials that are well known in graph theory. So there's something called the all-terminal reliability, which measures the probability that in a network, all the vertices can communicate. And this was a topic that I was introduced when I was a master's student at the University of Toronto by Professor Colburn, who was an expert in the area. So as an example, we have a network here. It's an undirected finite graph. The vertices are always working, but each edge is operational independently with probability P. And then we ask, what's the probability that all the vertices can communicate with one another? That is that the spanning subgraph of the operational edges contains a spanning tree. And for this graph, it turns out to be, you could write as 16p cubed times 1 minus p cubed, and that's enumerating all the states with 3 edges being up. 16 happens to be the number of spanning trees in the graph, plus 15p to the 4th, 1 minus p squared, plus 6p to the 5th, 1 minus p, plus p to the 6th. And you can see very quickly that this is a polynomial. In fact, the all-terminal reliability of a graph is always a polynomial in the edge probability p. Chromatic polynomials, a different kind of polynomial. It enumerates the number of proper k colorings of a graph, where a proper k coloring of a graph is an assignment of one of k colors to each vertex in the graph in such a way that if 2 points are joined, then they receive different colors. So for example, in this graph, which I call a diamond, it's the complete graph from 4 points minus a single edge. It's not too hard to see that the number of ways to color this with x colors is x times x minus 1 times x minus 2 squared. When x happens to be a positive integer, then this counts the number of ways to color the graph with k colors, with x colors, I should say. But because it turns out to be a polynomial in x, we extend this more generally to x being a real variable or x being, in fact, a complex variable. And we will come back to this. Particular roots or non-roots of certain graph polynomials relate to important graph parameters. For example, the smallest positive integer that is not a root of the chromatic polynomial of a graph G is what's called the chromatic number of G, chi of G. And finding the chromatic number of a graph has been well studied for well over 50 years, perhaps well over 100 years in graph theory. It's an important parameter. And that relates particularly to the roots of the chromatic polynomial. Now, you could ask beyond what positive integers are or aren't roots of a chromatic polynomial, because you can view it as a polynomial with complex coefficients, not only integer coefficients, but complex coefficients, you can talk about the complex roots of chromatic polynomials. We call those chromatic roots. And here's a picture of what the chromatic roots look like for all graphs of order at most 8. That means on at most 8 vertices. And you really get a beautiful picture. This is the picture that excited me and still excites me when I look at graph polynomials, trying to understand why the roots behave the way they do. Why are they located where they're located in the complex plane? Why are the real roots located where they are? And other questions about the nature and the location of the roots. So we see in this picture, for instance, the roots seem to be all in the right half plane. We also see that there are roots at certain integer points, but there are questions about what are the roots on the, say, the real axis? Are they always rational? What do their closure contain? What about the closure of the non-real roots? What does it contain? Are there certain zero-free regions on the real axis? Are there certain zero-free regions in the complex plane? Those are all fascinating questions. What about disks that contain all the roots? So those are all really interesting questions, both theoretically and perhaps for applied reasons. So polynomials can be useful tools in general as generating functions for combinatorial sequences as well. So we've seen 2 examples of useful graph polynomials, but the polynomials that arise for all terminal reliability and for chromatic polynomials arise from applied problems. So in a setting, the polynomials for certain evaluations have interpretations. For all terminal reliability, when the variable p is between 0 and 1, it gives you a probability, namely the probability that the graph is connected. For chromatic polynomials, when the variable is a non-negative integer, it counts something. It counts the number of proper colorings of the graph in that many colors. But in general, you can also form polynomials abstractly when you have a combinatorial sequence and you encode the combinatorial sequence as a generating function. And what you've done is translate a combinatorial problem into a problem that is, you can view as either algebraic or analytic. So we're going to talk in particular about one particular generating function related to a graph. And this is the one that I'm going to focus on for my talk. Let G be a graph, and I put in brackets finite and undirected because that's my assumption as we go forward. Then the independence polynomial of G, I write it as I of G of X, is defined to be the sum over all k bigger than or equal to 0 of I sub k times x to the k, where I sub k is the number of independent sets of size k in the graph G. And of course, a subset of vertices is independent if and only if it contains no edge of G. Independence goes right back to the initial study of graphs, and many authors have looked at independence from a variety of different points of view. You would think of independence as being a trivial notion in a graph, but really it's a very deep notion. Often when we have applications, independence has a particular important implication in terms of the interpretation of the graph. And there are lots of deep problems and deep areas that relate to independence. There's an area called well-covered graphs, which we'll come back to in a while, that looks at graphs where all the maximal independent sets have the same size. And that is a very well-studied area. Okay, so let's do some examples of independence polynomials. So if we look at the complete graph Kn, that's n vertices, all joined to one another by a single edge. What are the independent sets? Well, if you take any 2 points, there's an edge between them, so you can't take more than 2 points. So your independent sets are either of size 0, and that's only the empty set, and you get 1, or for each of the n vertices, they are independent, and so you get plus nx. Conversely, if we look at the empty graph of order n, that means that we're talking about n vertices with no edges amongst them. Well, then every subset is independent, and so the number of independent sets of size k will be n choose k if there are n vertices, and so you multiply n choose k times x to the k, and you sum it from 0 to n. because n is, of course, the largest possible size of an independent set in a graph of order n. And algebraically, of course, that's equal to 1 plus x to the n. What about if we take a complete bipartite graph with cells of size n? That's, we have n points on top, n points on the bottom, and all the edges in between. No edges amongst points in the top, no edges amongst points in the bottom. Well, what are your independent sets? Your independent sets are subsets of either the top or the bottom. So the generating function for a subset of the top is 1 plus x to the n, because there's n points there. Likewise for the bottom. So we add those two, but we've overcounted exactly one subset, the empty set, which has generating polynomial 1, so we have to take away 1. More interestingly, you would think, well, maybe all the formulas are kind of trivial. Well, if you do it for paths, you get a much more interesting formula. You get the coefficient of x to the k is n plus 1 minus k, choose k, and the sum runs from k equals 0 up to the floor of n plus 1 over 2. So a very interesting formula for paths, even a simple graph like paths. Now, generating functions efficiently encode a sequence of numbers as an algebraic structure that can be studied, therefore, with the tools of algebra and analysis. So what kind of tools could you use, and can you get something from algebra analysis that you might not be able to get otherwise just from combinatorics? For example, there's a beautiful, beautiful theorem that you may not have seen before due to Isaac Newton, which states the following. Suppose that you have a sequence of positive terms, a0, a1, up to an. Now, we say that the sequence is unimodal. That is, it's non-decreasing and then non-increasing. So it's going up and then coming back down. And that's something that combinatorialists love to investigate for sequences, because they often, counting sequences, have this property. Then it is unimodal if the generating polynomial, the sum of a sub I x to the I, has all real roots. So this is so fascinating that if you're interested simply in the shape of the coefficient sequence in terms of that sequence of positive terms, you form the generating polynomial and you look for something analytic about it. Where are the location of the roots? And if the roots turn out to be all real, then you find out that the sequence is unimodal. Beautiful, beautiful theorem that has had actually many applications in graph theory and combinatorics. We'll come back to that in a little while. We'll investigate the roots of independence polynomials to give a flavor of what kinds of interesting questions and results can arise. So we're going to be interested not only in what independence polynomials can say about independence in graphs, but we'll be interested in the roots of these polynomials simply because they have roots, and roots of polynomials are interesting. So I hope to convince you of that in general for graph polynomials in this talk. That's one of my aims. So as a little aside, independence polynomials can be applied to music theory, which is what Dr. Kumar indicated at the beginning of my talk. So we have, I and an ex-PhD student of mine have a paper where we illuminate this connection between independence polynomials and music theory. And as far as I know, it's the only connection that's been drawn between the two. So let me explain to you the connection. For a circulant graph of order n with distances 1 through d. So what is a circulant graph? You take the integers mod n and you join 2 points if their difference mod n is in the set 1 through d. So here's an example where we take the circulant graph of order 9. The vertices are the integers in Z9. And the distances here are 1 and 2. So d is equal to 2. You get a very symmetric graph. In fact, it's vertex transitive. And it's regular. It has lots and lots of nice properties. So myself and my ex-student Richard Hashino proved the following. We wanted to look at these graphs and see if we could find a formula for the independence polynomials of these graphs. So as long as n is at least d plus 1, then we found a formula. And the formula is, it's the sum k equals 0 up to the floor of n over d plus 1. You get a binomial coefficient, n minus d times k, choose k, and it's multiplied by a fraction, n over n minus d times k. So that gives us a formula for these independence polynomials, which is of interest in its own right. Finding these formulas, it's non-trivial to find these formulas. And as a corollary, if we look in particular at the circulant on Z12 with distances 1 and 2, we get the following formula. And if we expand it out, we get 1 plus 12x plus 42x squared plus 40x cubed plus 3x to the 4th. So why did I pick that one in particular? It follows from this formula that if you wanted to count the number of independent sets of this graph, we get 98, because the way you count the number of independent sets from an independence polynomial is you simply set the variable equal to 1. So we conclude the following. Now take the interpretation that the vertices are no longer Z12, but they're standing for, in Z12, the 12 notes from the equally tempered 12-tone scale of Western music. So in that, with those as being the vertices, we see the one-to-one correspondence. And now what we're going to do is join pitch classes, which are what the vertices are, if the pitch classes are close, if they differ by 1 or 2 semitones. So and there's a notion that if you listen to pitch classes that are close together, people tend to find it, if they're very close together, to be harsh. And this is a subjective feeling that people have. And some people have a broader tolerance for this kind of dissonance. And they find that if, is 2 semitones apart for pitch classes dissonant, that's hard to listen to, or consonant, they sound good together, that differs. If you listen to country music only, you will find perhaps 2 semitones apart is still a little harsh for you. If you listen to jazz, you might find that acceptable or even pleasant. So depending on that, if you found, say, distances 1 and 2 to be rather harsh, then what you'll do in Z12 is join them by an edge, and the edge indicates that they're incompatible in the sense that they're dissonant together from your point of view. And then you find that there are 98 possible consonant chords, good sounding chords. And a chord is a collection of notes that can be played together without any dissonance. So consonant chords correspond exactly to independent sets. So this is the great thing about our application of these circulant graphs to music theory. And so if you take away the 55 trivial chords consisting of either 0, 1, or 2 pitch classes, we find out that there are 55 of those and out of the 98. So this allows us to count nice sounding chords. And you could change this not only in terms of what you find consonant and dissonant in terms of the 12-tone scale, but you can even extend this, as music theorists have, to n-tone equally tempered scales, where the semitone is no longer defined as a ratio of 2 to the 1/12, but 2 to the 1 over n, if there are n notes in your scale. And you have that kind of extension by looking at these independence polynomials. Okay, we're going to come back to independence roots, which is going to be what I'm going to talk about for the rest of my talk. The roots of the independence polynomial are called the independence roots of the graph G. So, for example, I've done a plot here of the independence roots of all graphs on order at most 9. So on graphs at most 9 vertices. We get, from my point of view, a really beautiful picture to look at. And what I want to do is understand the picture and understand what is inherently true from this picture for all graphs and their independence roots, and what might only be an artifact of the fact that I've only gone up to order 9. The problem is that, we don't have any good algorithms for finding independence polynomials. And in fact, my staff and my student, Richard Hoshino, proved that in general, finding independence polynomials is an NP-hard problem. So that's computationally difficult, intractable. And in fact, we proved that except for the evaluation at 0, for any complex number, evaluating the independence polynomial at that complex number is going to be NP-hard. So you're unlikely to be able to efficiently find independence polynomials, let alone find their roots. But we can still maybe say something about the roots. So what do I see from the picture that's of interest to me? I see that the roots seem to be all in the left half plane. I see that the roots don't seem to have very big imaginary part. They're all bounded in absolute value by at most 4. The roots, there seem to be roots going out along the negative axis. How far do they go? I can't tell. Seem to be some roots along the real axis that are approaching 0. There seems to be maybe some little 0 free regions, maybe around the number -1. The questions that arise are the roots dense in the left half plane? We've only looked at graphs of an order at most 9. So we want to see and find answers to all these questions, and then find out, you know, what can we attack, and even more importantly to me is what are the deep theorems of analysis, old theorems due to the masters of analysis that we might apply to these independence polynomials and their roots. So the roots are really quite interesting and beautiful. But what can they say about the nature of independence in graphs? So this is going to be what are the applications of independence roots and considering them? And what can we say, on the other hand, simply because we want to look at the roots? So here we have a definition that we've seen earlier. We'll say a real polynomial, a0 plus a1x plus a2x squared plus dot 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 plus anx to the n, is unimodal and in absolute value. And so we mentioned this before. If in absolute value it is first non-decreasing, then increasing in terms of the coefficient sequence. That is, if you take the absolute value of the first coefficient, it's less than or equal to the absolute value of the second coefficient, and so on up to a certain point, and then it decreases. You could have some being equal, but it has that shape. And this includes as extremes that the sequence might be always increasing or always decreasing. It's called log-concave if the square of any term is bigger than or equal to the product of the two surrounding terms. For sequences that are positive, it's not too hard to see that log-concavity implies unimodality. Why would you be interested in log-concavity? It seems like a much more involved definition, a harder definition maybe to apply or to prove. The key thing is that for unimodality, you may be unsure of where to conjecture the peak is. For log-concavity, you don't require knowing where the peak is. If you prove something is log-concave, it will therefore be unimodal and have this kind of shape, even though you don't know where the peak is. And that's the advantage of looking at log-concavity. Now, not all graphs have unimodal independence polynomials. It was an open problem for a while, and Paul Erdős and some other people proved in a really beautiful paper that not only are independence polynomials not unimodal, but they can be what they call unconstrained. You can actually have them have dips and peaks wherever you like. So they can be, you can actually, in their terms, you can take a permutation and decide on the ordering of the coefficients. Are there some operations that produce ones that are? So this is a question that once you know that they can be non-unimodal, you'd ask, are there some families or some operations that will produce ones that are unimodal? So myself and another ex-PhD student, Ben Cameron, looked at the following operation. If you have a graph G, we're going to form what's called the graph star of G by attaching to each vertex V of G a new vertex V star with an edge. So essentially, we're going to attach a leaf to a new leaf to each vertex in a graph G, no matter what G looks like. So here's a little picture of G. I haven't drawn in the edges, but I've marked the vertices. If this is my general graph G where there might be edges among some of the vertices, the graph star would look like this. We would attach to each vertex a new vertex as a leaf. So for a graph G and positive integer k, what we're going to do is iterate this operation. Let gk star denote the graph k star of G. That is the graph formed by iteratively performing the graph star operations k times. So when we do it just once, we get the graph star. And if you're doing it more than once, what you do is you do the star operation iteratively that many times. So for k equal to 2, you take the graph star, and then you take the star of that graph. So as an example, let's look at the following graph. I have a little animation. Here's the path on 4 points. We do the star now, join a leaf to each one. Now we join a leaf to each vertex again, and so on. Okay, so we have a little theorem here that the following is true. If G is a graph and K is sufficiently large, so that depends on the roots of the independence polynomial, but the independence polynomial of G have some fixed roots, then eventually the independence polynomial of the K star of G is log-concave and therefore unimodal. So here's an example. I've drawn a figure here in a little animation. We take a path on 3 points, and what I do is substitute for each vertex an independent set of size 50. So I get a very big graph. And what I'm doing here is I'm taking the K star. And notice, I'm just showing some of the roots here, or in particular one of the roots here. Notice that the root starts off even in the right half plane, but eventually the root ends up in this little sector that I've drawn in blue. And that little sector between the top blue line and the bottom blue line has argument or angle 2 pi over 3. It's going from 4 pi over 3, from 2 pi over 3 to 4 pi over 3, or 120 degrees to 240 degrees. That's a key thing, that the root ends up in here. And in fact, all the roots eventually for the graph K star of this graph end up in that region. So what does that do? So the proof uses the following extension of Newton's theorem. Remember, I mentioned Newton's theorem says that if you have this generating polynomial where the coefficients are all positive and the roots turn out to be all real, and if they're going to turn out to be all real because the coefficients are positive, that really means that the roots turn out to be negative numbers, all negative numbers, then the sequence is unimodal. But really what Newton proved was that the polynomial was log-concave, and therefore the sequence was unimodal. And there's an extension of that due to Brenty, Royal, and Wagner that says that if all the roots of a polynomial, real polynomial f of x, are not just on the negative axis, but they're in this sector that I've drawn in green, then the polynomial is log-concave. And it's not a hard result to prove. And so the argument that I and my student Ben Cameron had was that we could prove eventually for the K star of any graph, the roots get pushed into that region. And we were interested in this K star because there's a conjecture that if a graph has a property of being well covered, that is that all the maximal independent sets have the same size, maximum mean with respect to containment, then the sequence of independence numbers is log-concave and therefore unimodal. So we can prove that this operation, the K star, always gives you graphs that have the property that they're well covered. In fact, they're very well covered. All the maximal independent sets have size half the number of vertices. Okay, so we have seen that the location of the roots in certain regions can inform about the shape of the coefficient sequence of the independence polynomial. That was the unimodality that we proved by proving that the roots were in the sector. What can be said about the location of the independence roots? So myself and my first PhD student, Carl Hickman, and another colleague, Richard Nowakowski, proved the following kind of surprising result. The set of independence roots of all graphs is dense in the complex plane. Now think about this from my initial picture that I had before. Remember, all the roots happen to be in the left half plane. We couldn't find a single root in the right half plane for graphs up to order 9, but that is an anomaly of only looking at graphs of order at most 9, of small graphs. And it's like this law of small numbers that, there are many coincidences when you only look at small numbers. And the coincidence there was that the roots were only in the left half plane. In fact, we could prove that the roots were dense in C. And again, here's the picture. This is of roots, independence roots of order at most 8. They're all in the left half plane. You don't see any roots that have big imaginary part. you see no roots in the right half plane, but in fact, the roots fill up the entire complex plane. So this is rather surprising, given that in the plot, there are no roots to the right of the imaginary axis. So let's focus in on that. A graph G has no independence in the right, independence roots in the right half plane, which I'll write as abbreviated as RHP, if it has at most 10 vertices. This is a difficult computation to do because you have to find the independence polynomials, which takes a lot of time. There are a lot of graphs of order at most 10. And then you have to find the roots and check where they are. And in fact, we could do another computation for all trees, in fact, up to 20 vertices, and find out there are no roots in the right half plane. So for quite far, you can't find any roots in the right half plane, but we know that the roots are dense everywhere, and in particular in the right half plane. So a polynomial with all its roots in the left half plane, which I'll abbreviate as LHP, is called stable. A polynomial with a root in the right half plane we'll say is non-stable. And we'll say a graph is stable or non-stable based on the stability of its independence polynomial. Stability has a long history in analytic function theory, and in particular, engineers have been interested in stability of polynomials in terms of dynamical systems. Stability tells them in a dynamical system that everything will get dampened down and will settle down, while non-stable functions tend to have chaotic behavior. So in particular, if the roots in the different colors here are independence roots, then if the roots are the black roots and they're independence roots for some graph G, then that would be a stable graph because all its roots are in the left half plane. If its roots are the red roots, the independence roots, then it'll be non-stable. And of course, the roots are symmetric about the real axis because we have a polynomial with real coefficients, so the roots appear in conjugate pairs. So myself and my ex-student, Ben Cameron, looked at stability of independence polynomials. We proved that if the independence number is at most 3, the independence number is the maximum size of an independent set, i.e. it's the degree of the independence polynomials. So if the independence number is at most 3, then the graph G is stable. All its roots are in the left half plane. Interesting question about how you might prove that, because there's lots of different graphs with independence number at most 3. But I'll refer you to one of our papers. What about independence number of at least 4? Well, myself and my ex-student proved the following really contrasting result, that it fails, that the roots are always in the left half plane. We proved that if the independence number of a graph G is at least 4, and you take any r bigger than or equal to 0, so this will be our notion of being far, and sufficiently large m, that if we take the graph G and we join the graph, a complete graph of order m. Join means take m points with the graph G and throw in all the edges in between. Then this has independence roots with arbitrarily large real part, that is real part greater than r. So it's out past r to the right. And the corollary is that if the independence number is at least 4, and you take, and G is, then G turns out to be a subgraph of a graph with independence roots, arbitrarily large real part, but with the same independence number. Because when you join a complete graph, you don't change the independence number. So we can do this, keep the degree of the polynomial the same, and still find independence roots, not only in the right half plane, but as far out to the right as we like. So here we see the graph. We're taking just 4 independent points, the empty graph on 4 points, joining large complete graphs, and you can see here what happens to the roots. Eventually they begin sneaking into the right half plane, and m was going from 1 to 25. Okay, and how do you go about proving something like this? Well, the proof of roots with arbitrarily large real part relies on the following old results from analysis. So we've already seen some old results from analysis, going all the way back to Sir Isaac Newton. Here we're going to see some other classic results from some of the top people in analysis. So here's a theorem due to Hermite and Bieler, and you've probably seen Hermite's name if you study orthogonal polynomials. Suppose that we take a polynomial p of x. We're going to break it up in a very natural way into what we call an even part and an odd part. So what you do you split it up into a polynomial in terms of the even powers of x. Now, if it's a polynomial in terms of the even powers of x, you can view it as a polynomial in x squared. So that's what we're going to call the even polynomial, p even. And then we take the odd part, we factor out an x, and then we get a polynomial just in terms of even powers of x, and that's therefore a polynomial in x squared, and we write that as p odd. So every polynomial can obviously be written in this way. We say that it's standard, and what standard means that it's either identically 0 or has positive leading coefficients, so very weak conditions. Then p of x is stable if and only if both the even polynomial and the odd polynomial are standard. They both have only non-positive all real roots. And furthermore, the odd one interlaces the even one. And I won't go into exactly what the definition means, but interlacing is like what I'm doing with my hands here, that if you take the roots of the odd one and the even one, the odd ones are in between the roots of the even one. So all those conditions have to hold for a polynomial to be stable. So we're going to use that. And notice as part of that, the even polynomial and the odd polynomial, if it's going to be, p of x is going to be stable, they have to have all real roots in particular. So the other theorem that we use that becomes very helpful to us is a theorem due to Gauss and Lucas. And I'm sure Lucas was a big name in analysis, but there is no bigger name in classical analysis than Gauss. And they both independently prove the following. Let f be a non-zero polynomial. It can even have complex coefficients. Then the roots of f prime, you could ask, where are the roots of the derivative of a polynomial? And the roots of the derivative, in particular, if f happened to be a non-zero polynomial with real coefficients, and if the roots of f happen to be real, then it's easy to see that the roots of f prime are real. More generally, what Gauss and Lucas proved is that if you have a complex polynomial, non-zero, then the roots of the derivative are contained in the convex hull of the roots of the original. So every time you differentiate, the convex hull of the roots becomes nested inside the ones of the original. And so we could use these two theorems to prove our result that eventually that if you take the join of any graph with independence number at least 4, its independence polynomial will have roots as far out to the right as you like. Okay, finally, we're going to turn to independence roots and graph operations. One of the natural operations is called the lexicographic product or the graph substitution. So the notion of the lexicographic product or graph substitution is a very old graph operation that's been used in many instances. It's been looked at for chromatic theory. If you've studied something called perfect graphs, which is a very deep area of graph theory that was extensively studied in the 60s, really up to present time, this lexicographic plays a central role in it. If you're given graphs G and H, the graph G composed with H, or I'll say it's the graph G with H substituted in for each vertex, formed by substituting H for every vertex of G, is formed by replacing each vertex V of G by a copy H sub V of H. And for every edge of G, we're going to join every vertex in the copy H sub U of H that we substitute for U to every vertex of H sub V that we substitute for V. So you can think of it as replacing vertices by these copies of H's. When there was an edge in G between two vertices, we throw in all the edges in between. And when there wasn't, we don't throw in any of the edges. Okay, so this has been well studied in practically for every graph operation and every graph parameter. So for instance, if we take K2, two vertices joined by an edge, and we substitute an empty graph of order n for each of them, empty graph here, we throw in all the edges in between, we get the complete bipartite graph K sub n comma n. Okay, so how does independence polynomials behave with respect to graph substitution or this lexicographic product? You might think, well, there's no correlation between the independence polynomial of the graph product and the independence polynomials for G and H. But you would be wrong. There's a deep connection that we can make enormous use out of. So the independence polynomial of G with H substituted in for each vertex is given by the following. We can actually write it down. What you do, the independence polynomial of G composed with H, it's the independence polynomial of G, and we substitute for the variable X, the independence polynomial of H minus the constant term 1. So for technical reasons, which you can read in the thesis, the PhD thesis of my ex-PhD student, Carl Hickman, we will work with, instead of the independence polynomial, we'll work with a very closely related polynomial. We'll write f sub g of x, which is the independence polynomial minus the constant term 1. That really changes very little in terms of the independence roots, but it's a technicality that will simply make some of the statements and results a little easier to state. So the question is, can anything be said of the roots of reduced independence polynomials when you repeatedly substitute G in for itself? So I'm just keeping track of the time. So I did this as an experiment probably about 20 years ago. I sat down the computer. My expectation was when I did the substitution, the roots would be all over the place. They would be all over the plane. So I did an experiment where I took the path on 3 points and I repeatedly substituted it in for itself. And then I looked at the reduced independence polynomial and looked at its roots. And I expected it to be scattered, to form no pattern at all. And this is the picture I got, and it struck me as soon as I got it. It looked like this. And if you've done any reading in analysis, what will strike you is what struck me back then is this looks like a fractal. And in fact, I did other examples and found out it again looked like a fractal. And it's an interesting question of how you generate these pictures, because as you do this graph substitution, you will find that the degree grows very fast. And so finding the roots becomes, or approximation of the roots becomes a non-trivial problem. And you can't find the roots exactly, so you have to approximate them. But even so, and I won't go into the details, but you can make use some mathematics to improve your algorithm drastically to find approximations for the roots when the graph gets high. So this is why I could go up to 11, get this beautiful, beautiful picture of a fractal. We can look at the limit of the roots. So that's just one, but you can look at the limit as the product grows higher with respect to the Hausdorff metric on compact subsets of C. And so I won't go into the details of that, but that's a well-known metric for compact subsets of the complex plane. So if we look at the limit of the roots for graph G of these iterations, they always form a fractal, we could prove. And we call this the independence fractal of G, f of G. And it is in particular the Julia set, if you've seen that term in analysis, of the reduced independence polynomial. So let's look at some other pictures, because I love looking at independence polynomials and their pictures. And here's another graph, very simple graphs. This is a point union a single edge. And you would think that's so trivial, it would have no interesting independence roots for its iterates and for its independence fractal. Fascinating picture again, another fractal. Here are just 4 copies of an edge, and you iterate it, you get this other snowflake-like picture. And here for 3 copies of an edge, look how different it is. You get a fractal, it's got 3 pieces to it, and yet unlike the other ones, it doesn't seem to be connected. It seems to be going into what's called fractal dust. So how do combinatorial properties of a graph relate to topological properties of the associated fractal? This is what I like to do, is connect up the mathematics, the analysis, to the combinatorial properties of the graph. So myself and my 2 co-authors could prove that if G is a graph with independence number at least 2, then if P is sufficiently large and we do a very simple operation of doing the join of P copies of G, eventually you'll get a fractal, an independence fractal that's disconnected. So this can form the disconnected, and you will find not only is it disconnected, but it's what's called totally disconnected. It has no connected components, breaks up into what's called fractal dust. We prove that if G as well is a graph with an independence number at least 2, if you take the join, so this is by accident, this is the same theorem. So let me go on to the next one. We could prove that if G is a non-empty graph, so it has at least an edge and has independence number 2. So I'm a very particular class of graphs, only looking at independence number 2, having n vertices and m non-edges, then we can actually find a box that will contain the fractal. The real part is between 0 and minus n over m. So that's the box for the real part. It's in the left half plane. The imaginary part also is 0 unless n equals to 3. So it's the box actually is along the real axis. If n equals to 3, what we get is a box with a certain height. The box is really squashed because if m is large, it's going to 0. We could also prove that if G is a graph with independence number 2, having n vertices, n equals 4 vertices, and m non-edges, then in fact the independence fractal, it's along the real axis, negative real axis from the previous theorem, and it's in fact equal to the entire interval from minus 4 over m to 0. Another theorem that we could prove is that if G is a graph with independence number 2 having at least 5 vertices and m non-edges, then we can't prove exactly what the fractal is, but it's going to be a dusty subset. That means it has no connected components, and it'll be between minus n over m and 0. Here is some other theorems that are relating the structure of the graphs to the connectedness of the fractal. The independence fractal of A times K sub E. So that's A disjoint copies of the complete graph on B points is connected if and only if B equals 2 and A is even, and it's totally disconnected otherwise. The independence fractal of K, A sub B, which is going to be the complete multipartite graph where each cell has A things in it and there's B cells, it's connected if B equals 2 and A is even, and totally disconnected otherwise. Furthermore, we can find a disk that contains the fractal, and it's going to be the disk centered at -1 with radius at most 1, and that this is best possible. So we're at the end of my talk. I'm going to end a little bit early. I will mention a few problems. Are the independence polynomials of all very well-covered graphs log-concave? I mentioned well-covered graphs are the class of graphs where all the maximal independent sets with respect to containment have the same size. So for example, a very well-covered graph is C5. You will find in C5, the independence number is 2. All the maximum size of an independent set is 2, and all the maximal independent sets, that is independent sets that can't be made any bigger by adding points, all have size 2. If you take any graph and you star it, you will find that it is a well-covered graph. And in fact, the independence number there is n over 2, if n is the number of points in G. And that's a very well-covered graph, because a very well-covered graph is a well-covered graph where all the maximum independent size, or all the maximal independent sets have size half the number of vertices. It's a question whether those independence polynomials are log-concave. There is no known example. And how can you make very well-covered graphs? Well, no one knows a construction that generates all of them, but the starring operation always generates out very well-covered graphs, starting with any graph G. Second problems. For alpha at least 4, can you characterize when graphs are stable? We saw when the independence number was at most 3, they're always stable. When the alpha is at least 4, there are some graphs that are not stable, in fact, have their roots as far to the right half plane as you like. So what about when alpha is at least 4? Can you characterize which graphs are stable? Another problem. Find sharper bounds for the maximum modulus of an independence root of a graph or tree of order n. So I haven't talked about the problem of what's the maximum modulus of an independence root of a graph or tree of order n. That's the subject of another talk where I have more time, but you can ask for that problem. And you might think, well, the growth rate of the maximum modulus, it certainly has to go off to infinity because we know that the roots fill up the complex plane. We can show that the maximum modulus, it doesn't grow linearly in n, it doesn't grow quadratically in n. It actually grows exponentially in n. And actually, if you take the log of the maximum modulus, we can show that log base 3 of that, we can show that that's approximately n. So it's growing like 3 to the n, which is really quite fast, but we don't have sharp bounds. And for trees, it grows like 2 to the n. So, but again, we don't have sharp bounds. We don't have any idea. Well, we have some idea, but we haven't proved what has the maximum modulus in either class of all graphs of order n or all trees of order n. And to characterize when the independence fractal is connected, we've looked at it for some very simple families of graphs. It's not easy to prove whether the independence fractal of a graph is connected, but we have managed to do it in some simple cases. Maybe there's a theory out there that talks about independence fractals and their connectedness in general. So I will end off on something else that's a very recent paper due to myself and my ex-student Ben Cameron, where we looked at the question of the following question. You can ask about certain kinds of roots. It's natural to look at, for a graph polynomial, the integer roots. It's natural, therefore, to look at the rational roots. It may be even interesting to look at the real roots. Amongst the non-real roots, you might ask about the roots that are purely imaginary, i.e. the roots that are on the imaginary axis. For many graph polynomials, it's not known whether there are any purely imaginary roots except for 0. So for instance, for chromatic polynomials, it's an open problem whether there are any purely imaginary chromatic roots. For network reliability, it's not known whether there are any purely imaginary roots except for 0, of course, in both cases. So what about independence polynomials? Well, in independence polynomials, the answer is really quite different. I and my student Ben Cameron could prove that there were purely imaginary purely imaginary independence roots. In particular, we can show often I and minus I can be independence roots when the independence number is bigger than 4. When it's less than 4, you can't find any purely imaginary roots except for there aren't any at all. In fact, 0 cannot be a purely imaginary root. It's never a root of an independence polynomial. And we've proved a variety of different things. We can look at purely independence roots, purely imaginary independence roots, where it's what we call purely imaginary rational roots, where the coefficient in front of I is a rational number. And we have some results along that. In any event, that takes me to the end of my talk, and I thank you very much.
Thank you, sir. As expected, the session with Jason Brown on getting back to your roots has been really inspiring. On behalf of STEP, RSIT, and participants, I express our sincere gratitude to Jason Brown for his valuable time spent with us and giving us an opportunity to take his thoughts forward. Thank you once again.
You're welcome. You're welcome. And now I just see there are some questions that if there's time, I could address them. Dr. Kumar, should I talk about them or?
Yeah, I read a question here.
Okay, so one of the questions was that many of the pictures on my slides were shown questions, especially about the roots, what kind of software was used to draw the pictures. I use a software package called Maple. I don't know how prevalent that is in India at universities. It's a software package very much like Mathematica, does the same kind of things. But Maple was developed by a number of mathematicians at the University of Waterloo. Since some of my collaborations have been with Waterloo, I've used this program since the 1980s. It's very easy in the program to find approximations for roots of polynomials and to plot them either as single images or as animations. And I know other people have used Mathematica, and some of my ex-students have moved from Maple to Sage and have used that to draw pictures of the roots. Are there any factorizations for these polynomials? Very interesting questions. And what might those factorizations mean? Of course, if you have the if you have a graph that's the disjoint union of two other graphs, the independence polynomial very easily can be seen to be the product of those two polynomials. I don't know if there are many other interesting cases where you get an independence polynomial that's a product of other two independence polynomials where it doesn't arise from the disjoint union process. But that would be a fascinating question. I know that question has been looked at for other graph polynomials in terms of, especially in terms of all terminal reliability, but that would be a fascinating question. So what about the question someone asked, is it possible to construct the graph from the polynomial? Very interesting question. You could say that a graph polynomial is independence unique if it is the only graph that has its independence polynomial. And in fact, myself, my ex-student Ben Cameron, and a current student, PhD student of mine, Ian Beaton, have written a paper where we look at this notion of independence uniqueness, and on the other hand, being independence equivalent, that they have the same independence polynomial. And we prove that while some graphs are independence unique, there are some graphs that have a very big family of graphs that are independence equivalent to it, that have the same graph polynomial. So I can direct you to that paper as well. So what is our motivation to seek log-concavity? The real motivation to seek log-concavity is one connection is to the connection to analysis, that if you're interested in proving unimodality, and there's a very famous combinatorialist, Doran Zeilberger, who says, he has a quote that says, combinatorialists love to prove unimodality for combinatorial sequences. That is what they basically like to do. So if you want to do that, then how do you go about proving unimodality? Well, if you know that the sequence, for instance, is symmetric, then you know that the peak is going to be towards the center, and then you try to prove that up to one point, up to the center, it's increasing or non-decreasing, and then non-increasing afterwards. But what happens if, for your unimodal sequences, the peak moves around, and you even have no conjecture of where the peak might be for a given graph? Well, then it seems lost to try to prove it being unimodal, but maybe proving log-concavity, which doesn't depend on conjecturing where the peak is the way to go. And you find often that where sequences are unimodal, they often seem to have the stronger property of being log-concave. So that's why you might want to look at it. Okay, one other question. Just like energy and characteristic polynomial, is there any term associated with independence polynomial? So I don't know. I think this is an interesting question. I think some people have looked at this notion of energy for other graph polynomials. I know that I've looked at another graph polynomial that's related to distances in the graph, and what you get from a certain evaluation of that, this is called the Wiener polynomial, is you get expressions for what's called the energy of the graph. I don't know if anyone's investigated that for independence polynomials. So I think that takes me to the end of the questions here. Yes.
Can I ask a question?
Of course.
Say, you know that there are several polynomials associated with the graph, like characteristic polynomial, chromatic polynomial, matching polynomial, independent polynomial. These are the most important. How do you compare the roots of these polynomials?
Well, it's
Is there
interesting.
any?
Sorry. Well, I think it's very interesting because I've had exposure. I've worked on many graph polynomials, and they motivate you to ask certain kinds of questions because of what's been found for other ones, and to look for similarities in terms of what you can prove about the roots and differences. So for instance, for matching polynomials, and matching polynomials are very closely related to independence polynomials. In the matching polynomials, at least one form of the matching polynomial, you're looking at the generating polynomial for the number of matchings of each cardinality. There is another matching polynomial that's often talked about that has some alternations in sign, but essentially they're very closely related. For that matching polynomial, it's often called the generating matching polynomial, the roots are always real. So very different from the independence polynomials. But independence polynomials, if you take what's called the line graph of any graph transforms the matching polynomial exactly into the independence polynomial. And so you end up with this class of graphs that have independence polynomial, the line graphs of graphs, that end up just on the real axis. So it's a very, very stark difference between them. But then you're looking at the difference between matching polynomials and independence polynomials. What it was to something that extended the notion of line graphs to graphs that are claw-free, that don't contain an induced star on 4 points. And those are called claw-free graphs. Someone conjectured that their independence polynomials were log-concave. First, they started off with unimodal, then log-concave. You know that the independence polynomials of line graphs are log-concave, and hence unimodal, because they have all real roots. And that was known for a long time. And so in a beautiful, truly beautiful paper by Chodnovsky and Seymour, they proved that the independence polynomials of claw-free graphs that don't contain claws, which contains the independence polynomials of line graphs, are indeed log-concave and unimodal. Very fascinating. They prove it by looking at essentially looking at the roots. Beautiful, beautiful paper. They prove that, in fact, that the roots are all real. I've often used, for instance, what I know about chromatic polynomials and what I've proved there, and what I've proved about independence reliability polynomials, to motivate me in terms of the questions that I ask about independence polynomials, and to motivate me backwards from independence polynomials to those other polynomials. And finally, I will mention that there is a 2-variable polynomial called the Tut polynomial that you may have heard about for any graph G. Some of the polynomials are simple evaluations of the Tut polynomial. So for instance, the chromatic polynomial is an evaluation of the Tut polynomial. The reliability polynomial is an evaluation of this 2-variable polynomial, the Tut polynomial. Independence polynomials are not. And so, you know, you might look for a common setting for those, maybe in terms of a multivariable polynomial. What they all turn out to be is you can talk about simplicial complexes and face polynomials of simplicial complexes, which turn out to be generating polynomials for the face numbers of simplicial complexes. And independence polynomials, chromatic polynomials, reliability polynomials all sit as evaluations of the face polynomials of simplicial complex. So in that sense, they are all in a common setting there. So I hope that's answered the question.
Yeah, Professor Jason, can I ask a question?
I have
Yes.
2 more questions if you have time. Yeah.
So someone go ahead.
What about the independence polynomial of G Cartesian H, Cartesian product of the 2 graphs? What is the structure of the independence polynomial? Is there any work going on?
I think there is work going on. I haven't looked at that. There are many different graph products, and people have looked at various graph parameters, various graph polynomials for things like Cartesian products. I believe there's a paper out there that deals with those kind of things. I don't think there's a nice way to write down the independence polynomial, the Cartesian product of 2 graphs in terms of the independence polynomials of each of the parts. But there are some results known in terms of various families, and that's as much as I can direct you to. But there are so many interesting questions to look at for independence polynomials, and that's certainly one of them.
I have one more last question.
Yes.
How about graphs uniquely determined by independent polynomials?
So I did talk a little bit about that. So you can look at, say two graphs are independence equivalent if they have the same independence polynomial, and a graph is independence unique if it's the only graph up to isomorphism that has its independence polynomial. We've done a whole paper on that, myself and an ex-student and a current student. Even looking at things like paths and cycles, it's fascinating. Even looking at cycles and saying some cycles are independence unique, some cycles aren't. Some paths are and some paths aren't. Some of these have very large classes of graphs that have the same independence polynomial. But I'll direct you to that paper to see the results there.
So can I ask?
The talk was excellent.
Thank you.
Yeah, please. Vinod,
Yes.
carry on.
Yeah. Professor Jason, is it true that the independence fractal will be always the Julia set of z square plus c for some c?
You mean the Julia set, of some?
Yeah.
Right. That I don't know. That I don't know. So I think that's a fascinating question. There's so many interesting questions surrounding independence fractals. What can you say about the dimension?
Yeah.
The way that these turn out to be independence fractals is essentially this. What is the connection to fractals? You can form a fractal by taking a polynomial and looking at the inverse orbit of a point. So that means that you look at f to the minus k. So you look at the things that end up at a point. So we look for these reduced polynomials. We look at the inverse orbit of 0. What things end up under inverse iterates at 0. And so, but I've had difficulty finding, so there are theorems that will help you decide the question of whether the fractal is connected or not depends on the inverse orbit of critical points for that kind of setting. I haven't found any good setting that talks about things like dimension for those fractals that are constructed in that way. If there's a theory there or a theory waiting to be developed, they will tell you things about dimension. But I think, it will rely on people who have a stronger background than me in analysis and who know more about fractals to find some more interesting stuff about these independence fractals.
Thank you, Professor Jason, for the enlightening and very informative talk.
Okay, thank you very much. It's been a huge pleasure. It's been my first talk in India. Even though I'm far away, would have been nice to do it in person, but given the circumstances, I really do appreciate the chance to do this, and I'm happy to carry on conversations with people. I can be reached at jason.brown@dal, D-A-L, that's short for dalhousie.ca. So I look forward to carry on conversations.
Thank you. We will be in touch. Thank you.
Bye-bye.
Bye.